Good day, stat students. So today we're going to go over section 3.3, and I keep on talking about how the observations, when they're clustered around the line very closely, that we have a strong relationship, and that when they're spread out, we have a little weaker relationship. So we're going to go over that and how to measure that, okay? And so what we're going to go over is what's called the correlation coefficient here. So now, as you saw in these two examples, we had a negative relationship, and so we have a negative slope. So slope by itself, though, cannot indicate whether a relationship between two quantitative variables is strong or weak. All right. The slope is a rate that gives us the average relationship. That's really important. Okay. So the slope is a rate that gives us the average relationship between x and y. But by itself, it doesn't tell us how strong that relationship is. It just tells us what the average relationship is. All right. So that's an important thing, but we gotta kind of combine it with something else. Okay. And that's where Pearson's correlation coefficient comes into play. All right. Now, I underline correlation coefficient because a lot of people just drop the word Pearson's. Pearson was the guy that created it and came up with it. And so his name is he decided to put his name on the front of it. Well, a lot of people just drop that and just call it the correlation coefficient or even just correlation. Okay. The symbol that we give the correlation coefficient is R, and it is a measurement from the entire data set indicating how strong of a linear relationship there is between two quantitative variables. Okay, so it's a linear relationship. So if you have a parabolic relationship, you're not going to use correlation coefficient to figure out the strength of that relationship. The relationship has to be linear. Okay, has to be able to be described by a line. All right. So like I said, the symbol is R, and the values that R can take on are from a -1 to a +1. And so let's go through what that means then. And so I can't stress this enough. The sign of R indicates the type of relationship, not how strong it is. All right. So a negative doesn't mean anything bad. Actually, all that a negative R indicates is a negative relationship between X and Y. That's it. It doesn't tell us that we have a weak relationship, the negative sign. Negative R indicates a negative relationship. As X goes up, Y goes down, and that's it. Doesn't indicate anything about the strength yet. A positive R indicates a positive relationship. Doesn't necessarily mean anything good. Okay. What you have to take a look at as far as the overall strength is how close it is to a -1 or a +1. An R that is close to a -1, say an R that is less than, say, a -0.75, that's indicating a pretty strong negative relationship. An R that is close to a +1 indicates a strong positive relationship. An R that is close to 0 indicates no relationship. Okay, and so the closer we are to a -1, the better. That's indicating a strong negative. The closer we are to a +1, just as good. Okay, strong positive. The closer we are to 0, not too good then. That relationship, not too strong. So we could say that something between a -0.75 and zero point 0.4 is moderately strong negative, and something that is between, say, a -0.4 and 0, weak negative. Okay, then you can kind of flip it for the positives. All right. Now the slope and the correlation coefficient are very much related to one another, and you're going to see this when we go ahead and show you the calculation for the correlation coefficient, and we kind of extend it out. Slope of the correlation coefficient will have the same sign every single time, but it will be very unusual for them to have the same value. Okay, so they'll have the same sign. So if R is negative, so will the slope. If the slope is positive, R will be positive. Okay, even if one is 0, the other one is going to be 0. Okay, and so the sign is always going to be the same. All right, so graphically, let's take a look at this stuff. And so this would be an example of R of a -1, a perfect, what we call a perfect negative relationship. All the dots are right on line, no deviation from the line whatsoever. Okay, be honest with you, we wouldn't even use statistics in this situation. We would use algebra because we have a deterministic uh, model, perfect positive relationship. Okay, slope is positive, R is going to be positive, all the dots are on line, perfect positive relationship. No relationship. Okay, so R is getting very, very close to 0 at this point. All right, so let's take a look at some uh, data that I just generated in StatCrunch and see if what you think about the correlation here. So I'm going to get my pen out, I think. Maybe not. Oh, well, let me get my pen out. Try it again. There we go. There we go. All right. Well, I kind of already gave it away here, but we have a positive relationship. Okay, dots are a little spread out, but not too far spread out because they're pretty close here. Get a little bit further apart here, but not too far, right? And so we have a positive relationship, and the correlation turned out to be a 0.89. Pretty strong positive relationship here. Okay. How about this one? This one, we clearly have a negative relationship. Okay. And the dots seem to be a little bit more spread out than the last one. Okay. So what do you think about this one? Is it going to be close to a -1 or closer to 0? I think it's going to be closer to 0. And it turns out to be a -0.29. Okay. How about this one? We have a positive relationship. Seems to be awfully strong, right? So this is going to be pretty close to 1, isn't it? Yeah, this is a correlation of 0.99. So just to sort of help us match up the histograms with the correlation coefficient. All right, here's the formula for the correlation coefficient. And it's 1 over n minus 1 times the summation of the multiplication of a bunch of z-scores. Okay, and so if we extend this out, now z-scores can be applied to not just population stuff, but also sample stuff. And so here we have x minus x bar over sample standard deviation for x, and then multiplied by the corresponding stuff for y. And so x bar is the sample mean for x, y bar is a sample mean for y. The s sub x is the standard deviation for x, and there's our standard deviation for y. Okay. So now here's the formula up in the corner, and I'm going to go over the example that I did in the last section when we calculated the slope and the y-intercept for our paired data. Okay. Remember, our x bar was equal to 3, our y bar was equal to 4, and obviously there's our origin there. Okay. So what happens here is that by subtracting x bar, so by doing this formula here, by subtracting x bar, okay, and y bar, what it does is that it basically temporarily shifts the origin away from 0, 0, and it actually shifts it over to whatever x bar, y bar is. In this case, 3, comma 4, right? 3, 4. And so think of the origin not here anymore, but actually shifted up to here, okay? That actually plays a big part in how the correlation coefficient works, okay? So let's move on here. So if you remember when you used to talk about like quadrants when it comes to the origin, that you had a quadrant 1, quadrant 2, quadrant 3, quadrant 4. Well, if you're up in this quadrant up here, let's read this. It says if both of these values here are positive, okay, and when you multiply them, the product's going to be positive, okay? So if it just so happens that x bar and excuse me, if x and y are both greater than x bar, y bar, when you do the multiplication between these two, okay, the product of that's going to be positive. Well, if you're down here in this quadrant, if both terms are negative and you multiply them, well, let's see, two negatives multiplied together, it's going to produce a positive. So if you get values here in this quadrant, and then you get values down here in this quadrant, when you do the multiplication, it's going to turn into a bunch of positive values then, okay? Well, what happens if we're in these quadrants? Well, what's going to happen here is that one of the values is going to be positive and the other one's going to be negative. And so when you multiply these z-scores, you're going to get a negative value, okay? So if your values happen to be here and happen to be here, you're going to get a bunch of negative values for the products of these z-scores, okay? And so you can imagine then, if you have a bunch of values here, okay, you're going to get a negative correlation. If you got a bunch of values that are in these two quadrants here, you're going to get a positive correlation. So that's basically how this works, okay? So here is our data set, okay? And so let's go ahead and plot them. And so this is 0, 0. I haven't moved the origin just quite yet. So there's 1, 8. There's 2, 6. There's 3, 4. Okay, 4, 0, and 5, 2. Okay, so I went and plotted them. All right. Now our x bar is equal to 3, y bar is equal to 4. And so if you can see that, I went ahead and shifted the origin from here up to there. Okay. So now think of that as that being the origin, and these are the different quadrants. Notice, where do our values pretty much lie in? They lie in the quadrant that's going to produce negative here, okay? This one is actually sitting right at the origin because we had a value of 3, 4, okay? So we have most of our values that are going to be negative. So this is definitely going to produce a negative correlation, okay? Okay. So back to the formula. Here's the thing is that it's kind of a pain to calculate the correlation by multiplying a bunch of z-scores. It really is, okay? And so I prefer not to do that if we had to do this by hand. And so what I want to do here is I'm going to do a little bit of algebra, okay? Now, you got to be careful in other formulas. Just I can do this because the sample standard deviation for x and the sample standard deviation for y are what we call constants in this formula. And I can move the summation sign just simply up to the numerator because we're not, we don't have to sum basically in the bottom. And so I can move the summation up to the top there, and it makes this formula so much easier, okay? And so notice there that now the numerator for the correlation coefficient is the same as the numerator that we saw for the slope. Okay, I told you they were very much related to one another. Okay, and so we already calculated that for this data, right? Remember doing this for the in the last section. Okay, and it turned out to be that the numerator turned out to be a negative 18. Okay, what about the denominator then? Okay, so we have this the sample standard deviation for x, sample standard deviation for y. That should be easy actually based upon what we already have here in our data table. I'm just going to move it over. And remember the, well, I didn't mean for all that to pop up at once, but it did. Sorry about that. Here's the sample standard deviation formula up here, okay? And so notice that here's the deviations already. And so what do we got to do? We got to square the deviations, what I've done there, okay? And it turns out to be that the numerator is 10. So we have 10 divided by 4 because we have an n of 5. And so when you do that math, that turns out to be 1.58. Okay. So there's the sample standard deviation for X. We got to do exactly the same thing, but for Y. Okay, so I went ahead and changed everything over to Y. Okay, so notice these are Y's now. Here are the Y's. When we do exactly the same thing, so we're going to take this column here, square it, okay, which is showing up over here now. And remember, all positives now. We add them up, we get 40. Okay, there's the numerator. Denominator is still going to be 4. So we have 40 divided by 4. We hit our square root button. Square root of 10 is 3.16. Okay, so now we have our sample standard deviation for X, sample standard deviation for Y. And that'll be part of the denominator there. We still have this n minus 1 outstanding. We know that's 4. Okay, 5 minus 1, 4. And so we have 1/4 times that stuff over on the right-hand side. Okay, and when we calculate that out, that turns out to be a negative 0.9. That is so much easier than multiplying a bunch of z-scores. Okay, especially if we already calculated the slope. Okay. So before we leave this, so obviously we have a strong negative relationship, and we saw that from our scatter plot, especially when we moved the origin from 0, 0 over to 3, 4. Okay. All right, some thoughts regarding the correlation coefficient. First of all, it does not depend on the variable's units. Slope does. Okay, slope units matter quite a bit. Okay, but the units don't necessarily matter with the correlation coefficient. For example, if we measured things in pounds and then changed everything over to kilograms, does it change the correlation between them? No, of course not. Okay, that relationship, how strong that relationship still exists. If we changed over from, say, inches over to yards or yards to miles, doesn't matter. Okay, the correlation is going to be exactly the same. But as soon as you start changing the units, the slope will change, the value of the slope. Okay, it does not matter which variable is x and which variable is y. It does for slope. Okay, certainly that would change the slope. Okay, but that would not change the correlation coefficient. The correlation is not resistant to outliers. Neither is a slope. Okay, correlation is not resistant to outliers. So let's take a look at that. Right now, let's go back to our example where we had a very strong positive relationship. Okay, and our correlation is right now 0.99. Well, let's do this. Let's add this guy right down here. Okay, what do you think that's considered here? Hopefully you say that's a outlier. Okay, because it bucks the trend, right? We expected x to be larger for larger values of for x, and it turned out to be pretty small. Okay, so went against the trend. Now look what the correlation did. It's down to a 0.5 where it was before 0.99. So that one value took the correlation from 0.99 all the way down to 0.5. Okay, so the correlation is definitely not resistant to outliers. Okay, let's continue. A strong correlation, this is important. A strong correlation does not prove causation between the explanatory and response variables. They just might be linked mathematically somehow. Okay, let me give you a real crazy example, but hopefully it kind of proves the point. So let's say that we took a look at monthly suntan lotion sales versus monthly shark attacks. Okay, if you went ahead and took a look at this, there's actually a strong correlation between the two. Okay, sounds kind of funny, right? But there is. As suntan lotions sales goes up, we tend to, that's probably a good indication that we're going to the beach, by the ocean, right? And so on and so forth. And so as more people congregate into the ocean, more monthly shark attacks. Okay. Now there's reasons for that. Okay, there's reasons for that. We'll talk about that here in a second. But um, let's think about this. So a strong correlation, but we aren't saying there's something in the ocean that's making the sharks attack. This is not Sharknado. Okay, the sharks aren't jumping out of the ocean just because we're wearing suntan lotion. Okay, there's got to be something that's mathematically linking these things. Okay, and probably, in my simple thinking, it's probably things like temperature or something like that. As the temperature goes up, okay, what do we like to do? We like to be outside. We like to go to the beach. And if we go to the beach, that means going to have to put on suntan lotion. But also as the temperature goes up, what's happening to the water? The water is temperature is going up. The fish tend to go to that, will expand and go into that those waters. And well, what is the sharks going to do? They're going to follow their food source, right? They're going to follow those fish, and then all of a sudden, humans collide with sharks. Now, that's my simple thought of it. I'm sure marine biologists would say it's a little bit more complicated than that, and that's fine. But as you can see, uh, we have these two variables. Okay, we have monthly suntan lotion sales and monthly shark attacks. Okay, but there's another variable or variables in between that's mathematically linking them. Okay, temperature and maybe some other things. Okay, and so what we call temperature and those other things. Okay, are what's called lurking variables. They're variables that we do not measure. Okay, we know that they're there. Okay, um, but we're not measuring them in our study. Okay, but we know they're there and they're linking these guys together somehow. Okay, all right. So that ends our presentation for 3.3. Thank you.